Hey everyone, I'm Adam Kellaway from Dow, and here to talk about Ray for distributed mixed integer optimization at Dow. So the tagline, like not just for ML, is really just to like get you into this, pack this full room. But just kind of showcasing like how we're using Ray for something that is like adjacent to ML, so to speak. So I've had a lot of great talks all day with the keynotes as well about real ML workflows and ML use cases. Here we're sort of showcasing how we're using Ray to distribute another type of math model. So before that, a little bit about me. I'm an AI tech lead for Dow's Digital Fulfillment Center, which is our innovation center for all things related to supply chain, where I focus on ML and optimization in that space, so deploying models, building models, et cetera. And then my formal background is in mixed integer programming with PhD in chemical engineering from University of Minnesota, and before that a master's at Imperial College in London. So let's talk a little bit about production scheduling. In general, so I kind of assume like the audience might be more diverse and like not necessarily have experience with what we're doing in a large kind of legacy chemical manufacturer like Dow. So Dow operates these world-scale industrial chemical manufacturing facilities, and production scheduling is about managing what products to make when, right? And so in general, you may have seen these big, massive chemical facilities. I come from Houston. If you have ever been in that area, you know what I'm talking about. And so for these production schedules, in general, for the business that we're working with, you have to maintain a 90-day planned schedule. So that plan is subject to change, but you have to maintain the schedule. You can't just arrive at work one day and decide, like, what are we going to do with these multi-billion-dollar like installations. In each of these sites, there are multiple reactors. So you can think of a reactor like a machine that does a bunch of stuff, and it's like your base unit. So each one of those reactors has to have an individual schedule assigned. And in the business that we're working with, each reactor can produce between 10 and 20 products, right? So that's each of those products is qualified to be made on each of these units or each of these machines to the appropriate grade that we require to sell to our customers, right? So each reactor can only make one thing at a time, but that's where that 10 and 20 is just like the total number of possible products that they can each make. That sort of scales the problem that we're going to talk about in the next few slides. And then the other complication that we'll see is that the products certain products can be shared amongst reactors, right? So on a single site, you can think of it like a customer, so to speak, comes and says, I want 1,000 pounds of product A, and it's up to a planner or scheduler to say, okay, I can make that product A on reactor 1 or reactor 2. How do I split it up? And then what consequences does that then have to all the other demand for all the other products and the other types of schedules, since each reactor can only do one thing at one time, okay? So a simple example here would be, so now I've gone from my 10 to 20 products to 4 ABCD. I have a product mix, and I can give you a transition matrix, right? So here's classic like transition matrix going from product A to product B. It's going to cost us like 15 units, right? So it's discrete. No matter how long you've made A4, when you go to make B, it's going to cost you 15 units of cost, right? No matter too much about the units here. Notice that it's in general not a symmetric matrix, and those big red X's indicate that certain transitions are completely not allowed, right? Now you can, right, find a cycle using a variety of approaches that minimizes the total cost and visits each product at least once, right? And so that's our minimum transition cost. In this case, I think I've done it right. It's just A, B, C, A, B, C, D, and then back to A, right? And the thing here, though, is that the total cost that we incur when we run these operations is partly transition costs and partly also inventory costs. So inventory comes out when you sort of start to unroll this product wheel. So we call it product wheel. You can clearly see why. And so we unroll this product wheel into a Gantt chart, right? So schedule here, time going left to right. So you can either unroll it, like you can spin this product wheel very quickly, and you get the top Gantt chart, right, where short runs, and then you're producing product A, and then in a very short period of time later, you're back to producing that product A. Or you can have these like longer campaigns. Each of these blocks is known as a campaign. And you have longer campaigns and goes more slowly around your product wheel. It may take you 30 days or 60 days to go all the way around, and that has a different impact on inventory. Note here that the blocks in general are not, don't have to be the same size, right? So it's just, I'm not a great artist. So in general, they could be different sizes. So you may have A being longer, and then B being shorter, and then C being slightly longer again. So the difference between these two is that if you turn over that inventory quicker and you're going around this product wheel faster, you're going to have many more transitions, so higher transition costs, but much less or much lower inventory costs because you're turning over that inventory a lot quicker, right? And then the opposite is entirely true, vice versa for the longer duration. And so you could sort of put that together and see that like I can just run a search here over the different possibilities of how fast I'm going around these cycles, and then trade off like my inventory costs and my transition costs to some low operating cost like minimum there, right? And so legacy approach for the business, they've been doing this approach for 20, 30 years, is to hand design that product wheel initially, and then to do some simple calculations to figure out what that minimum operating point is. So if you're clever, like me, or like all of us, you may have noticed that like there's no reason why we have to design that product wheel separate from the like operating point and the campaign lengths, right? So there's no reason, I said you have to visit each product at least once, but you can visit products more than once if that's gonna impact your total lowest operating cost. So what we do, we propose a solution to the business, and we said, look, we can create here a mixed integer linear program to solve together both the product wheel design problem as well as the campaign length problem as well. So like both the design of the wheel as well as how fast you're going around that wheel to minimize a total cost objective. And so we do that, and then sort of spoiler here is that we're going to use Ray to distribute that solution, and that's going to increase our solution time from a sort of naive approach by up to 10 times. So quick review for the mixed integer linear experts in the room. It's a relatively straightforward MILP model, a bunch of constraints that you would expect: inventory balance, product transition, product family mix, min-max campaign length, so additional complexities there that I haven't talked about. Essentially, we formulate this whole thing in Pyomo, which is a Python-based like framework to write these kind of problems, and we solve it with Gurobi commercial solver to solve these types of problems. The chase here is though that the problem doesn't scale very well. And by scale, I mean not necessarily what we talk about scale all of the rest of today, but here it's just that when I go to larger number of products, for 4 products, it works fine, but for 10 or 20 products in each of these reactors, it takes too long to solve, right? So eventually it will solve it, but it can take an hour or 2, and that's too long for the use case at hand, where the use case at hand is like users are gonna come into this system and they're going to create these input scenarios, and they're going to run the model, get the answers back, and then you can evaluate it, do a different type of scenario, run the model, get the answers, and sort of compare and contrast the different scenario input files that we generate or that we can use. And so that needs to be like an hour is too long for these users to sort of wait to get an answer when they need to run many different scenarios to trade off different additional complexities that are not included directly into the model. So that's why we decided to introduce a hybrid sampling and simulation approach, and then we use Ray there to distribute those independent samples. So the hybrid approach is one where we sample the number of campaigns in for each product. So we determined that was like really our blocker like integer variable here. So if you can just sort of you can fix those integer variables for the number of campaigns for each product, then when you end up solving your problem, it solves significantly faster. So we go from hours to like seconds, basically. So what we end up doing is we randomly generate a campaign sequence. If it's feasible, then we go and solve this like sub-problem to the original mixed integer linear problem, collect the result, and then repeat that until I've achieved some target number of samples, right? So there you think kind of Monte Carlo style, like 1 is not enough, but like 100,000 is probably too many. Like, have you covered your space evenly to reasonably say that you found the minimum? I think of it also like kind of like a global optimization to a certain degree, where like you're picking a lot of these local mins and you're trying to find the overall best solution, and then we output the best result at the end of the day. So an illustrative set of results here. So you can see like the legacy approach, hand calculation on the product cycle, very simple wheel, right? Very simple product cycle, just once through every product. Now our hybrid approach is able to find much more exotic cycles, right? So here you can see we're visiting many products many times. We sort of almost have like 2 sub cycles going on here. And the results, I wanted to put numbers on here. They told me I cannot, so we're just gonna have to go with this. But basically, like the legacy approach is significantly longer to do the same amount of work. Inventory costs are a lot higher because it takes a lot longer to like cycle all the way around. Whereas our hybrid approach will have, by observation here, like clearly higher transition costs, but on the balance, the total costs we are on the new approach significantly cheaper than the legacy approach. So what I like about this, though, is that as these transition costs and inventory costs change with the market conditions, you can just rerun your model, and you may have a different result every single time versus the legacy approach. That's a lot harder to achieve. So a more complete example now, so you can see now I go back to introducing my multiple reactors or multiple lines into a big site. So somewhere along the supply chain, production scheduling, like production planning cycle, someone's going to tell us as planners, okay, I need all of these products from this site in approximately this quantity per month, right? So I think of like forecasting and things like that. And then as a planner, I have to decide, I do my demand allocation model there where I have to decide like how much of that demand do I allocate to each of the reactors. And then for each of those reactors, each of those units, I have to then solve that product wheel optimization sequence problem that we just talked about. So we end up with call them two agents. Demand allocation model, which I haven't talked about today, that is also a mixed integer problem. We don't use Ray to do anything necessarily with that one, but then that produces inputs to these sub-models, these agents 2s, or product cycle optimization models. And so you can see clearly, like already start to see how each of those is now independent, so you can think, how am I going to distribute this out? So I can showcase that here, where in blue here, like the demand allocation model produces these inputs. These are all independent to each other, and each one of those models goes through that sampling approach. So I have to sample a bunch of solutions. If the solution is feasible, then I'm going to solve that MIP model, and then I min across the samples that I find. So again, you can see like every single row of these, you can see where we're going, right? Every single row of these is independent, and that's where I'm using Ray to distribute each one of those sample and solve steps independently across whatever cluster I have to solve this large problem. I'm aiming for about 500 solutions per reactor, and that takes about 100,000-ish samples per reactor. So the ratio of like feasible, like how many samples you need to run to get enough feasible samples will depend on the particular problem at hand, like how tight the transition matrix is and other types of constraints as well. So because I felt like I needed to put some code up here, I put super simple Ray code on here. This should be very familiar with folks that are, kind of basic Ray at all. So imagine I have some hopefully you can read it. I have some function called get sample and solve here. It's a remote function. I'm importing it. It takes a data here. So I'm going to kick off a bunch of those. Maybe I kick off like the number of CPUs that I have in my cluster. Just a starting point. And then in my while loop, I'm going to use the ray.wait functionality to get a result back. If it's feasible, so if this solution solved is true, then I add it to my set of results, and I increase the number of solutions that I found by 1. And then either or, so if the result that comes back from my Ray wait call, if that says like, hey, you didn't find a solution, you didn't find a feasible sample, then I'll just, either way, I'll kickstart another one of these like get sample and solve things. And I keep doing that until I have some target number of solutions, so that's where that 500 comes in. So our current architecture to deploy this, so we're in Azure Shop at DAO today. We have like a web app that's a traditional web app that our users are using, and then they kind of hit a submit button, and that sends a bunch of input data to an Azure machine learning batch pipeline. So that is, if you're familiar with that, that's just a batch pipeline. So it exposes an endpoint that just allows the users to hit that and kind of kickstart a batch job, right? And so that batch job is on AML compute clusters. We're using 4 nodes. They have 8 CPUs each. So we kind of kickstart that. We spin up the compute cluster. We put Ray on it. We pull the model from it, the model registry. We run our thing across these 4 times 8 CPUs. And then we get a result back, and then the result hits an endpoint in the app service to store the results to whatever database is out there. We don't love this architecture, so we'll talk about that in a bit as well. But if you're familiar with Azure Machine Learning batch pipelines, like this compute cluster, if it's shut down, you have to incur this spin up time, which is 4 to 5 minutes easily for a model that can take a minute or 2 to run, right? So from a user perspective, it's not as fast as it could be, but it is cheaper for us to run, and we'll talk about some future work in a few slides as well. What am I doing here? I got plenty of time. So just a set of results here to showcase the speed up that's possible. So you have the time in purple against the left-hand axis, and then the cost against the right-hand axis in green. So you can see, as I increase my number of CPUs that I have, I get a significant decrease from single node type operation. Doing this type of in sequential mode, right? So imagine I'm doing my sampling now, and I'm doing like one sample at a time. Is it feasible? If it is, solve. Then do the next one, or that would probably shoot up way higher than what I'm showing here today. So this is just purely the Ray solution and just showing you like the scaling. So what we're seeing, quick decrease initially and then a tailing off, that I'm sure is a factor of like at that scale, you're hitting the limits of like the communication overhead is outweighing the actual like work that you're doing. And we would not run 192 CPUs for this work. We're targeting right now, I think 32 CPUs per run, just as like a fine balance between how many and how much time it takes to run. But what's nice is you can showcase like cost here increases linearly-ish, and so you can get a significant speed up without a massive increase in cost because of Ray, right? So we love that. What's next? So summary here, quick summary before I talk about future work. So we formulated these two independent agents. We talked about for a production scheduling problem. We're using this hybrid approach where we're simulating and then we're optimizing for the product cycle optimization. And then there is that decomposition, which we haven't talked about today, for the demand allocation model. We're parallelizing and distributing the solution of the scheduling problem with Ray, right? So we're deploying this today. Currently, it's deployed to all of the plants that can use this technology and generating significant value. Again, similar comment, I wanted to put some numbers in there, but they told me I'm not allowed to, which is fine, because at the same time, I was nervous that the numbers I would put up for folks in the room that work for significantly larger companies, you'd be like, that's a joke. Well, fair play. For us, it's a lot. We like it. It's this project, it's very important for us, and it has a lot of attention, and it's won a bunch of internal awards as well. The point in red, I think, is key, and I'd like to have more discussion here. Kind of end of the day, happy to just, I'm nearly finished, so I have plenty of time for questions and offline and things like that. But the idea is, like, to me, Ray, we use Ray a lot, and like the open question is, like, what other problems in mixed integer space could benefit from either the hybrid approach that we showcased, but even just Ray in general, where I think, cloud compute, super easy to spin up a compute cluster, but it's always been harder to do that distributed computing. We heard it this morning in the keynote. That's not surprising. So then especially for folks like me who are more like mixed integer practitioners and not computer scientists who don't know how to do distributed computing very well, I see Ray as an easy solution to enable us to think kind of in that distributed approach. So again, like if there's any, thoughts or discussions, happy to have that at a later stage. So the future work, we would love to move to RayServe, and again, a kind of open discussion here because we like a bunch of stuff that RayServe offers, especially for, because we still have a bunch of business logic, maybe, a bit of I/O as well that we can run separately and leverage, what RayServe kind of offers us. But I think the challenge with us is that we have these like fundamentally long-running things. So it's not ML inference, which is sort of sub-second style stuff. And I sort of threw again an example here. I don't love it. I kind of hacked it a little bit, and I've played around a little bit with it, but happy to, I'd love a discussion further of like, okay, you have this long-running job, and how do you kind of integrate that in a RayServe? What's the best way or easiest way to run that within the RayServe kind of ecosystem? Would love that discussion if there's experts in the room or after or whatever. And then the future work in general, right? What our group is doing at Dow and what our supply chain, digital supply chain vision is to have many of these multiple decision-making agents, right? So some of them are humans, some of them are computational. In the computational space, they could be business logic, they could be ML, they could be RL, they could be mixed integer type problems. But the idea is that all these different agents can interact with each other seamlessly to address these like challenges such as faster decision-making, globally coordinated decision-making, and kind of deal with these common or conflicting goals. So kind of get to decisions faster. And so we think that the Ray ecosystem, like I say here, that's my vision certainly for the group, is to go further and deeper in the Ray ecosystem, serve, RL lib, et cetera, et cetera, et cetera. And I think that's it. So happy to take questions. Thank you very much. Reach out to me here, online, wherever. Email me. Yeah, thank you very much.
Nice talk, Adam. Just had a small question. Like you said, you generate like 100,000 proposals, and most of them turn out to be like not following the constraint. have you ever tried any supervised learning or any RL-based approach to sample these? Is it just randomly sampled using some distribution?
Yeah, we just randomly sample, but it's a great idea. So I may bring that back to the team to see how we can do smarter sampling. We're currently are looking at improvements to the actual just pure mixed integer problem to make it maybe just run by itself. But that's a good idea for the sampling. We do there's some level of intelligence to how we're sampling, but nothing like ML, RL style. So it'd be super interesting to check that out though.
And how much would it help if you don't have to generate 100,000, maybe just 10,000 samples from some intelligent sampling approach? Would that
it would reduce the time, because basically the most of the time is spent searching for these, finding infeasible samples and then never solving. So there's a minimum time where okay, how long does it take to solve 500 of these things? So, but beyond that, all the rest of the time is wasted essentially. So yeah, if it was the higher the ratio of samples to feasible solutions, it would speed it up. And we find that some models that are easier just by the nature of themselves do solve significantly faster for the same number of samples. So this one I showed here is just to get a separation that was nice. I ran a more complicated one for that graph that I showed for the speed up, for example. But a lot of them the ratio is better than what I showed.
Right.
So a speed up would help significantly.
Okay, thanks.
Thank you so much. This is a beautiful solution. I have two questions. The first one is regarding the structure of the MILP problem. So let's say the travel cell TSP problem is very different from the structure of a scheduling problem. So do you see the generalizability of how you generate, let's say, the cuts or the sampling? Does it generalize to more MILP problems? And the second question is regarding uncertainty. Do you factor in uncertainty in your solution, and what methods like Monte Carlo, or what methods do you use?
Yeah.
Thank you.
Okay, I'm going to address the second one with the uncertainty. We don't do that. So this comes at a part of our work process in supply chain where once every quarter, they want to get to that level. So right now it's once a year, once every 6 months. They run this type of problem, and they've been doing this for, like I say, 20 years. They run the problem, and then they get a baseline, that baseline schedule that I showed. And then day by day, a human being will adjust the schedule based on uncertainty. Okay, we thought the demand was here, but it's lower or higher, whatever. So for that approach, and I've spoken at previous race summits around our project called AlphaDAO, which is that next layer where now we're dynamically using RL to train an agent that would take into account a lot more the uncertainty and the hedging and things like that go on the uncertainty of actual demand arriving, versus this is at a slightly higher level. With the vision is that these two would work together. So this would set a baseline schedule, and then an RL agent can do that dynamic day-by-day adjustment for the users. Yeah. So in the first question with the generalizability of it, I think this was a very we had a problem. We wanted to do mixed integer. We have a lot of mixed integer experts in the company, and they sort of took the first approach. And they were okay, taking a little too long, and then we just sort of took this naive approach of just this is the worst integer variable, so let's sample it, and that'll save us a significant amount of time. So the generalizability, we haven't looked into it. I do believe that, in general, the marriage of Ray with mixed integer is a very powerful one. So there's lots of other mixed integer things where you're doing subproblems and decompositions, and you're looping over basically independent subproblems. So why not, instead of just doing a sequential loop, distribute it, right? And then use Ray. Again, like I say, to me, it's the ease of use, right? So a person like me, who's not a computer scientist, doesn't know how to distribute computing, but now I can do it. So I think this is introducing Ray to more and more mixed integer folks and seeing what they do with it. I think it was super exciting for the field. Yeah. Thank you.
Hi, I have two questions. The first one, so once you generate the sample, does the problem become an LP, or do you still have to call Gurobi or a MIP solver to solve the sample?
I believe there's still some integers that we need to solve for afterwards. It's not fully LP.
But are you still going through Gurobi?
Okay, so we're not going through Gurobi. So because we want to do these like a lot of samples, and we've only purchased Gurobi license for 2 at a time, so we use an open source GLPK to do that. So we don't need the power of Gurobi anymore because it's a like simpler problem, and then we don't have the licenses to do all the samples in parallel, basically. So yeah, that's the simple answer. That
makes sense, thanks. And then the second question, do you know how much worse is the gap between the old approach and the new approach?
We think so. That's the case of like how we feel like we're not that far away. I don't have an actual number to say like, okay, like the true optimum is this, and then the the new approach is this. I think we're not that far away. Our business people are very happy with the solutions that it's spitting out. There's additional like post-processing that happens. So subtlety, but like there's additional post-processing that happens where the business actually wants less transitions overall. So we collect all the solutions that are within 5% of the best thing that we found, and then we return the one that has the lesser transitions. So there's like these subtleties that make a lot of that like maybe like more challenging to calculate. But it's a good idea to maybe track like for each model run, track the full model, just let it run in the background. We don't care for the user, and then compare afterwards as like a monitoring approach. But we haven't done that. That's a fair suggestion though.
Got it, thanks.
Hi. When you talk about transition costs, does that refer to just the cost of stopping the production of product A and then starting the production of product B, or is there some kind of direct synthesis from product A where you can carry over like excess inventory?
Yeah, so it is exactly that, like just the amount of money we lost going from A to B. So it's not like, so these are polyethylene production runs, so they're continuous process. So we sort of slowly move the process by tweaking the inputs from making like quality A to quality B, and then there's like that period of time in between that like we call it off grade. So it's like, we don't throw it away, we sell it, but we sell it at a lower cost, a lower price. So basically like that gap between prime A and this off grade is like, that's what factors into that transition cost. So additional constraints around like minimum campaigns impact that transition cost. So if you were to run a product for a small amount of time, you can't basically do that. You have to like ramp up, and then some of the transitions are 0 off grade because basically what happens is if you run the subsequent product long enough, you can just like back mix, and the problem to your problem is just you just dissolve away all the excess stuff, so your overall quality is still where it needs to be. That makes sense. So yeah, it's not quite. I believe it's not quite as like discrete as what I'm showing and what the business like has always used. There's a lot more subtlety, like how long you've done it before and how good the people are and things like that. But we treat it as just a discrete number for now.
I had a question on after you use Gurobi with your 2 licenses to do the heavy lifting, have you looked at any stochastic local search processes where you swap either for a given reactor the order that you're doing things or across reactors and start with that feasible solution and then do these kind of perturbations?
We have not. That would be, yeah, that's like, we have not done that, no. So I guess you mean like in the sequence, in the schedule? Yeah, it's so it's a circle, right? So there's no beginning or end, even though we end up producing a Gantt chart which starts and ends in the place. So I'm not quite sure, but it'd be good to talk maybe offline about it. I'd be curious to see what you're thinking about.
Sounds good, thanks.
Yeah.